This lecture we're talking about the density function of a continuous distribution. So a continuous random variable x, cannot have a probability mass function. So the reason for this is that we have p x is equal to x equals 0, and this is for any value x. So this fact, although it's rather counterintuitive, it can be demonstrated in terms of the continuous random variable x that records the outcome of selecting a number at random from the interval 0 to 1. So the selection is random in the sense that any two subintervals of the 0 to 1 of equal length, right, such as 0, 0.1 and 0.9 to 1, they're likely to contain the selected number. So this implies that the probability x in an interval of length L, and this equals L. So for example, if we say the probability that x, the continuous random variable x, is between 0 and 0.5, right? It's equal to 0.5, right? And it follows this because if we have the probability of this continuous random variable between 0 and 0.5 is equal to that random variable, again, being between 0.5 and 1. And this is since the two intervals are, this is since the two intervals are of equal length, right? They're of equal length, and because, well, we have that random variable between 0 and 0.5 plus that probability of the random variable between 0.5 and 1, that's equal to 1, right? Since they're disjoint and their union is the entire sample space. It's the entire sample space. So that first relation, let's go back up to the first relation that I gave. The first relation right here. And then the second relation right here. So those two relations, well, that second one implies the first one, right? Because the second one implies the first one, because a single number is an interval of 0 length. So that second relation implies the first one because a single number is an interval of 0 length. So the random variable used to demonstrate that first relation is the simplest name continuous random variable. So we take a look at a definition for uniform in the interval 0 to 1 random variable. So we select a number from 0 to 1 so that any two subintervals of the interval 0 to 1 of equal length are equally likely to contain the selected number, and let that continuous random variable x denote the selected number. Then we say that X has the uniform in the interval 0 to 1 distribution, and denote this by writing what we have as such. All right, so again, if you go back to that second relation, right, that second relation that I wrote, it said P parentheses X in an interval of length L close parentheses equals L. That relation implies that the probability distribution of the uniform in the interval 0 to 1 random variable is known. So in fact, right, if we have the notation that we just mentioned, it's CDF, it's cumulative distribution function, sorry, CDF, is as such. We have F sub X of X is equal to P parentheses continuous random variable is less than or equal to X. Right, and then this is equal to, we have 0 if X is less than 0. If X is less than 0. We have X if X is between 0 and 1. And we have 1 if X is greater than 1. So in addition to the cumulative distribution function, the probability distribution of a continuous random variable, it can also be described in terms of its probability density function. All right, let's look at another definition. And here, the probability density function, or we can just call it the PDF, of a continuous random variable. Right, we'll call X. This is a non-negative function. Non-negative function. Therefore, if saying this fx x is greater than or equal to 0, it's greater than or equal to 0. So let's get that line out of the way there. For all x. All right, with the property that P x is being between A and B, right, equals the area under it and above the interval A to B. So with the property that this probability that random variable is between A and B equals the area under it and above the interval from A to B. Thus, P parentheses where x is between A and B equals the area under fx between A and B. Okay. So we can even present some typical shapes of probability density functions. Here, I'll show some right here. Want to be like this, call this what, symmetric. Another one, bimodal. We could have this one right here be positively skewed, and this one right here, this would be negatively skewed. Okay, so these are some typical shapes of probability density functions, PDFs, and they're shown to you right here in these typical shapes. A positively skewed distribution is also called skewed to the right, and a negatively skewed distribution is also called skewed to the left. The area under a curve and above an interval, right? The area under a curve and above an interval is illustrated in this next drawing that I'm going to make for you. So since the area under a curve is found by integration, so I'll first create the area under the probability distribution function, probability density function, I'm sorry. So here we have so this is, I'm going to state that it's the area under the probability density function above the interval a to b. In this illustration, we're showing that the area under a curve and above an interval looks something like this. So, as I was saying, since the area under a curve is found through integration, then we have P a less than x less than b is equal to the integral, where your limits are from a to b of f(x) with respect to x. Okay. So this is basically why integration is needed in probability theory. So for a non-negative function f to be a probability density function, the total area under the curve that it defines must equal 1. Right? So what I'm stating is the integral of f of x with respect to x from negative infinity to positive infinity is equal to 1. Right? So the total area under the curve of a PDF must equal 1. So if we take a look at our example, it says that if x, and we have the notation u 0, 1, we want to show that probability density function of x is as such. We have fx, and then we're going to have 0, 1, and 0, 0, 1, and 0. Okay, and the restriction here is if x is less than 0. Here, if x is between 0 and 1. And here, if x is greater than 1. All right, so we need to show that the definition of the probability density function that I wrote a few seconds ago, we need to show that that holds true. So since all the area under this function corresponds to the interval 0 to 1, right? 0 to 1, the area above any interval from A to B, inclusive of B, equals the area above the intersection from the interval A to B with the interval 0 to 1. So it suffices to show that it does hold, that definition does hold for intervals from A to B with A and B being between both 0 and 1. So for such intervals, right, we have from A to B, here we have it's equal to limits of integration r from A to B, 1 with respect to x equals B minus A. Okay. So by that second relation that I had given, right, P parentheses X in an interval of length L is equal to L, by that relation um, that was given, it's also true that P parentheses A is less than X less than B equals B minus A. So therefore, that definition that I read of and wrote of the probability density function, that definition holds.